Hi there students, it's Mr. Hatchcastam here, and today we're going to learn how to calculate relative frequency. Now we're going to hear these two words quite a lot during this lesson, so relative frequency and experimental probability. They essentially mean the same thing. They are the same thing, they're two interchangeable words. So if I say experimental probability or relative frequency, I'm talking about the same thing. Now, probability itself is the likelihood or the chance of an event occurring. And to calculate probability, we can think about the number of desired outcomes divided by the number of possible outcomes. And we'll do some examples to get our head around what we mean by probability. So over here it says write down the probability of the following events. So the spinner landing on yellow. So our desired outcome is yellow, and the total number of possible outcomes is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I was to work out the probability here, and if I can just get my pen to work, here we go. So we said the number of desired outcomes divided by the total number of outcomes. So we have 10 possible outcomes and 1, 2, 3, 4 yellow sexes here. So the probability of the spinner landing on yellow is 4 out of 10. So we can say probability of Y or yellow is 4 out of 10. Now, hopefully you're good at this. We can convert this into a percentage or a decimal. So 4 over 10 is the same as 4 divided by 10. A fraction is a division problem. So we can rewrite this as 0.4, or we can rewrite this as a percentage. Now, percent means per 100. So what I want to do is to rewrite this fraction as a fraction out of 100. So what I would have to do is multiply the denominator by 10, and I would have to do the same to the numerator. So 4 times 10 is 40. So 40 per 100 is the same as 40%. And given that 4 over 10 is equivalent to 40 over 100, then 4 over 10 is equivalent to 40%. So we can write probability as a fraction, as a decimal, or as a percentage. So if you ever saw a probability problem where you had a fraction or a decimal or a percentage, don't be put off by that, because these fractions, decimals, and percentages are essentially equivalent. Now, if I move on to the next example here, so what is the probability of drawing an ace from a deck of cards? Now, a deck of cards has 52 cards in it, and there are 4 aces. So the total, I'm just going to write actually, the probability of ace is equal to the total number of possible outcomes. So we can draw any of the 52 cards, but for that card to be an ace, there is only 4 possible outcomes. So we can draw the ace of clubs, the ace of hearts, the ace of spades, and the ace of diamonds. So here the probability is going to be 4 over 52. Now, if I was to do 4 divided by 52 on my calculator, I would get 0.076. So that is roughly that is going to be 7.6%. All right, so we have a 7.6% chance of drawing an ace from a deck of cards. And then over here we have rolling a dice and getting a 3 or more. So on a dice, there are 6 possible options. So probability of 3 or more. There are 6 possible options or 6 possible outcomes, and we want 3 or more. So that's going to include 3, that's going to include 4, that's going to include 5, and that's going to include 6. So that's going to be 4 over 6, which simplifies to 2/3, and 2/3 is equivalent to 0.6 recurring. So rather than writing 0.66, I'm just going to write 0.6 recurring, which is equivalent to 66.6%. Now, what we've calculated here is the theoretical probability, and the theoretical probability is what we would expect. So here, what I would expect is for our spinner to land on yellow 40% of the time. So here, what I would expect is for someone to draw an ace maybe 7.6% of the times. And over here, I would expect someone to roll 3 or more 2/3 of the time. So that's what we would expect. This is the theoretical probability. However, relative frequency or experimental probability is different to theoretical probability. Now let's start by thinking about a penalty shootout. So what would be the theoretical probability of our striker? I think this is Ronaldo. So of Ronaldo scoring or missing. Let's think, let's take all other factors and variables as being constant. So there is no pressure factor. We're not thinking about the skill of the goalkeeper. We're not thinking about the crowd. We're not thinking about the quality of our striker. We're just thinking, what are the two possible outcomes? Well, the two possible outcomes are either he scores or he misses. So we can say this is a 50-50 chance because he will either miss or score. So there are two possible outcomes. So we can say the probability of scoring is going to be 1 out of 2, or the probability of missing, again, is going to be 1 out of 2. But in reality, in this scenario, this theoretical probability is not a very accurate measure. And this is where experimental probability comes in hand. So that's the probability that is determined on the basis of results of an experiment repeated many times. So for us to be able to accurately estimate the probability of Ronaldo scoring, we would need a lot of data, or we would have needed Ronaldo to have taken a lot of penalties, and based on the number of penalties he had taken, we could then estimate the probability of him scoring. Now, in reality, this is some stats I looked at. Ronaldo in his career has taken 143 penalties and he's converted 123 of them. So this is the relative frequency, or this is the experimental probability of Ronaldo scoring, which would be as a percentage, so 123 over 143. So if I divide these two numbers together and multiply by 100, I can get the percentage. So this works out at just over 86%. And if I was to round my answer, it would just simply be 86%. So the relative frequency, or the experimental probability of Ronaldo scoring, is 86%. So 86% of the times he would score, essentially. And that's very much different to this probability that we've worked out here, 1 out of 2. All right, so let's move on. And again, this is just a formula to work out experimental probability. So the number of times the result occurs versus the number of times the experiment's been done. So here, the number of times Ronaldo has taken a penalty, I suppose we can think about that as an experiment. He's taken a penalty 143 times and he's scored 123 times. So the number of times Ronaldo scored divided by the number of penalties he has taken. And this is pretty useful when it's difficult to calculate the theoretical probability of an event. All right, so here's an interesting proposition then. Amy has taken 2 penalties this season so far and has scored both. In the next game, Amy's team are awarded another penalty. So this is what Amy's coach says. Since Amy has a 100% record, she scored 2 out of 2. The probability that Amy will score is 100%. Is the coach correct or not? Well, you can pause the video and think about this, but in reality, this is a false assumption, because Amy has only taken 2 penalties. For any experiment or for any event to be reliable, it would have to be repeated a number of times. Amy's only taken 2 penalties. So this statement here is not very accurate because we have a very small sample of data, we can say, or she's only taken 2 penalties. If she had taken, say, 100 penalties and she'd scored 100 of the 100 penalties that she'd taken, then we could say, yes, this statement is a fair statement to make. But because she's only taken 2 penalties, this statement is completely false. So for experimental probability to be reliable, an experiment has to be repeated a fair few times. So if you only repeat an experiment twice, that's not a very accurate estimate that you will find. And this is a really important bit to take away when we're talking about experimental probability or relative frequency. Remember, experimental probability and relative frequency are the same thing. All right, so here we have a question. The question says the table shows the number of times a coin landed on heads and tails. Estimate the probability that this coin lands on heads. So based on this, because the question says estimate, because the question says estimate, we need to calculate the probability from the results that we have obtained. So theoretically, the probability of heads and tails should be 5 and 5 or 50-50, because we can either get heads or we can get tails. So in theory, the probabilities are half, or 50-50, or 50%. However, because it says estimate, we need to use our results here. So the probability that the coin lands on heads is going to be 3 out of 10, because we've flipped the coin 10 times. So in total, we have 10 flips, and 3 of the flips were heads. Now the question says, is this coin fair? Well, at first glance, we could say the coin is not fair because it's more biased towards tails. We can clearly see it lands on tails a lot more. However, the experiment has only been done 10 times. So whilst on the surface it might appear that the coin is unfair or the coin is biased, however, the experiment hasn't been repeated enough times for us to make a conclusive decision here. If, however, we had, say, 30 tails and 30 heads and 70 tails, then we could say, oh, this coin is definitely biased in favor of tails. But because we have 3 to 7, that might even out if we were to flip the coin a few more times. So to answer this question, we can say, on the surface, yes, it appears to be biased in favor of tails. However, the experiment hasn't been repeated enough time to allow us to form a conclusive decision. All right, so let's move on to another problem. So here it says the table shows the number of vehicles that park in an underground car park during a single day. What is the relative frequency of cars? So relative frequency, again, it just means what is the experimental probability. Now again, experimental probability is the number of times a result occurs over the number of times the experiment has been done. Now in the context of this question, we want to look at the number of cars and vehicles that have parked in this car park. So the relative frequency will be the number of times the experiment has been done, or the number of cars that have parked up. So that's going to be 81, 84. And how many of them were cars? So 60 cars out of 84. So the relative frequency is going to be 60 over 84. And if we were to simplify this, we would get 30 over 42. And that would be 15 over 21. In its simplest form. However, as the question doesn't actually tell you to simplify, you can leave it as 60 over 84. However, it is good practice to always simplify your fractions. All right, let's move on. So over here it says, Andrew and Jenny played a game of chance. The results are recorded in the table. Whose results will give a better estimate for the probability of winning? So again, this goes back to this idea that the more we repeat an experiment, the more reliable the results will be. So Andrew has played the game a total of 63 times, whereas Jenny has played the game a total of 140 times. So actually, Jenny's results will give a better estimate because she's repeated the game more times. So if we were to write something here, we would say Jenny's results are more reliable because she has played the game more times. All right, so let's go on to the next question then. What is the probability of winning based on Jenny's results? So let's work this out. Again, this is working out the experimental probability or the relative frequency. How many times has Jenny actually played this game? So she's played 48 plus 192. That's going to be 140 times. So we can say probability of winning is equal to 48 over 140, which is going to be, oops, sorry, I'm totally wrong, aren't I? That should be 240. My apologies. Seems like I can't add today. So that's going to be 240. So we would get 48 divided by 240. And if we simplify this, that will give us 1/5. Now 1/5 as a percentage is going to be 20%. And you can convert this by, if we think about 1/5, we want to rewrite this as a fraction out of 100, as an equivalent fraction out of 100, I should say. So 5 times 20 will give us 100, 1 times 20 will give us 20, 20 per 100 is equal to 20%. So here's a bit of FDP, fraction decimal percentage conversions here. So 1/5 is 20%. So the probability of winning based on Jenny's results is 48 over 240, which is the same as 1/5, which is the same as 20%. So 20% of the times you would expect to win based on Jenny's results. All right, and I'm just going to rub out the workings that I've done here. And we can move on to the next question. Now it says, using the probability calculated from Jenny's results, if you played the game 100 times, how many times would you expect to win? So because the probability here is 1/5 or 20%, if we played the game 100 times, we would expect to win 20% of the times. Now 20% of 100, so 20% of 100 is simply 20. So from these results, we would expect to win 20 times. Now, if the question was, I don't know, if you played the game 80 times, the same principle will apply. So I'm just going to use a different color pen. Let's say if we were to change 100 to 80, we would still win 20% of the times. Now 20% of 80 is going to be 16. So if we played the game 80 times, we would expect to win 16 times, because 16 is 20% of 80. And remember, we got 20% by calculating the probability. The probability of winning is 20%. So however many times you play the game, you will win 20% of the time. So even if you played the game, I don't know, 200 times, 20% of 200 is going to be 40. So you would expect to win 40 times. All right, let's just rub this out. So the answer to C is going to be 20%. Sorry, not 20%, but 20 times, I should say. All right, do we have one more question? Yes, we do. So it says, what is the probability of winning based on both players' results? So in total, how many times have they played the game? So we have 240 plus 45 plus 18. That is going to give us 303. So they've played the game 303 times between them. And how many times have they won? They've won 58, 60, 66 times in total. So the probability of winning based on both players' results is going to be 66 over 303. And that might work out to be about just maybe under a quarter. So 66 divided by 303, that's going to be 0.217. If we multiply that by 100, that will give us approximately 21.7%, which is just under a quarter. All right, so if we move on to the next question, and I should rub all of this out. So this is an exam question I got from a past paper. It says, Stuart throws a biased coin 10 times, he gets 7 tails. Maxine throws the same coin 50 times, she gets tails 30 times. Prasha is going to throw the coin once. Whose results will give the better estimate for the probability that she will get tails? Stuart's or Maxine's? You must give a reason for your answer. So, again, we said the more you repeat an experiment, the more accurate your results will be. So we can say Maxine results. So Maxine's results will be more accurate because she has flipped the coin more times. And if we want it to be accurate, Maxine has thrown the coin 30 times compared to Stuart, who's thrown the coin 10 times. So she's done the experiment 3 times more than Stuart. So her results, we could say, are likely to be 3 times more accurate, if we wanted to be very precise here. Now it says use Stuart's and Maxine's results to work out an estimate for the probability that Prasha will get tails. So we've thrown the coin a total of, oh, sorry, my apologies. Maxine has thrown the coin 50 times. So she's done the experiment 5 times more than Stuart. So her results are likely to be 5 times more accurate. I said 30, but I should have said 50 times. I was looking at this wrong number over here. Now go back to question 2. Use Stuart's and Maxine's results to work out an estimate for the probability that Prasha will get tails. So in total, they flipped the coin 10 plus 50 is 60 times. And how many times did they get tails? So Maxine got tails 30 times, Stuart got tails 7 times. So that's going to be 37 over 60, which is over a half. So using these results, we would say the probability that Prasha will get tails is going to be 37 out of 60. Now, again, you could leave your answer as a fraction, as a decimal, or a percentage. All right, let's do some more examples. So here, another exam question. It says the probability that a biased dice will land on 5 is 0.3. Megan is going to roll the dice 400 times. Work out an estimate for the number of times the dice will land on 5. Right, so 0.3, that is the same as 30%. If we wanted to convert a decimal to a percentage, we simply multiply that decimal by 100. So 0.3 times 100 is the same as 30%. So what we know is that 30% of the times you will land on 5. So if we throw the dice or roll the dice 400 times, 30% of the times we should get a 5. So what we need to work out is 30% of 400. Now, 30% of 400, well, to work out 10% is going to be 40. So 30% is going to be 3 times 40, which is 120. So 30% of 400 is equal to 120. So 120 times the dice will land on 5. And another way of thinking about this is 30% is the same as 0.3, and the word of simply means multiply. So we could have simply done 0.3 times 400, and that's the same as 30. That's the same as 3 times 40, I should say, which will give us 120. So again, 120 times the dice will land on 5. I prefer to work with percentages because I think we read and hear about percentages a lot more. So generally, I find students are more comfortable with percentages. And when we talk about percentages, the context of the question becomes a bit more clearer, I find. So if you're comfortable with percentages, always work in percentages. However, if you just wanted the quick method, just understand that you could simply do 0.3 times 400. All right, now let's move on to another question, if I can. Here we go. So it says, Jack sows 300 wildflower seeds. The probability of a seed flowering is 0.7. Work out an estimate for the number of these seeds that will flower. So the probability that the seed will flower is 0.7. So we can convert 0.7 into a percentage by multiplying 0.7 by 100. That will give us 70%. So what we know is that the probability of seeds flowering is 70%. So we would expect 70% of the 300 wildflower seeds to flower. So what we need to do here is work out 70% of 300. Now 10% of 300 is going to be 30. So 70% of 300 is going to be 7 times 30, which is 210. So work out an estimate for the number of these seeds that will flower. Well, we would expect 210 seeds to flower. Right, boys and girls, so that's it. Key takeaways from this lesson is to understand the difference between theoretical and experimental probability. Theoretical probability is the probability that we would expect to occur. Experimental probability is the probability that we will obtain from repeating an experiment a number of times. And another key fact is that the more we repeat an experiment, the more reliable our results will be. And always, always, always remember that relative frequency and estimated probability are the same thing. So don't get confused by the terminology. Thank you for watching, and I wish you all a very good day. Bye.